Hello guys, my name is Sosimo Misa and welcome to our introductory presentation on queuing theory. So let's start. The basic question is, what is queue? Queue is a line or a sequence of people, vehicle, or any other things awaiting their turn to be attended to or to proceed to. I'm pretty sure we almost encounter such scenario in our daily lives, like boarding a bus, jeepney, or plane, lining up for public toilets, mag-withdraw o cash sa ATM, exiting a doorway at the end of the class, mag-order sa mga favorite fast food ninyo, and etc. But then, queues are not only present on people. For example, planes which are waiting for their turns in order them to fly in airports. While in transportation engineering, queuing can occur at red lights, stop signs, or traffic-based flow constriction. When not dealt properly, queues can result in a severe network congestion or gridlock condition, therefore making them something important to be studied and understood by engineers. Cumulative input-output diagram by Newell's curve. Based on the departure rate and arrival rate for data, the delay of every individual vehicle can be obtained. Using the input-output queuing diagram shown in the side figure, it is possible to find the delay for every individual vehicle. The delay of the nth vehicle is time departure minus time of arrival, T2 minus T1. Total delay is the sum of the delays of each vehicle, which is the area in the triangle between the arrival, AT, and departure, DT curves. Service method. We have first come, first serve, or first in, first out. Last come, first serve, or last in, first out. Priority, HOV bypasses at ramp meters. Characterizing queues. Queue length characteristic, it's either finite or infinite. Number of channels, number of waiting lines. For example, in supermarket, we can say 12 or more than 12. At ramps, it's either 2. And we use the following notation. The arrival rate represents lambda, and the departure rate represents mu, and the utilization rate is equal to rho is equal to lambda over mu. Degree of saturation. In traffic engineering, saturation describes the maximum traffic flow which can be handled by a junction. The saturation flow is the rate at which a continuous flow of vehicle can pass through a constant green signal, typically expressed in vehicle per hour or PCUs per hour. We can say that it's oversaturated when lambda is greater than mu, or undersaturated when lambda is less than mu, or saturated when lambda is equal to mu. Uncapacitated queues, MD1 model and MM1 model. It has been shown that queue size, waiting times, and delays differ between MD1 and MM1 queuing. These differences are represented in formula shown below. Note that a minor difference between the two. Average waiting time and average total delay and expected number of units in the system, including vehicle being served. In MD1 models, the average waiting time is equal to rho over 2 mu times 1 minus rho. And MM1 model, the average waiting time is equal to lambda over mu times mu minus lambda. The average total delay in MD1 model is equal to 2 minus rho over 2 mu times 1 minus rho. In MM1 model, average total delay is equal to 1 over mu minus lambda. The the expected number of units in the system in MD1 model is equal to 2 minus B, 2 minus rho times rho over 2 times 1 minus rho. And MM1 model is equal to rho over 1 minus rho. Uncapacitated queues, or MM1, random arrival and random services. The probability of n units in the system is equal to P to the power of n times 1 minus rho. Average waiting time of arrival including queues and services is equal to 1 over mu minus lambda. The average waiting time in queues including vehicle being served is equal to lambda over mu times mu minus lambda. The expected number of units in the system including vehicle being served is equal to lambda over mu minus lambda. Mean queue length excluding vehicle being served is equal to lambda squared over mu times mu minus lambda. The probability of speeding time t or less in a system is equal to 1 minus to the power of negative 1 minus rho times mu times t. The probability of speeding time t or less in a queue is equal to 1 minus rho times a to the power of negative times 1 minus p times mu times t. And the probability of speeding more than time in the queue given that the queue is not empty, and the probability of more than n vehicles in queue. Capacitated queues or finite. Queues permit a maximum number of vehicles to wait and thus have different properties than uncapacitated queues. For single channel undersaturated finite queues where the maximum number of units in a system is specified as n and with random arrivals and departure. We have MM1 model. The probability of n units in a system is equal to 1 minus p over 1 minus p to the power of n plus 1 times rho times n. Expected number of units in a system is equal to p over 1 minus p times 1 minus n plus 1 rho to the power of n plus n times rho to the power of n plus 1 over 1 minus rho n plus 1. Real life causes of queue. For roads, we have geometric bottlenecks, lane drops, hard curves, hills, accident and incident, traffic signals and intersection control, at gate crossing with other modes, railroad crossing, drawbridges, etc. Toll boats, ram meters, Gawker effects, inclement weather. For train and transit, we have platform capacities, fare gates, ticket windows or ticket machines, minimum separation for trains, security checkpoints, efficiency of trains entering and leaving station, number of tracks, switches, etc. For water and maritime, we have locks and dams, port capacities, minimum safe distance determined by government and physics, inclement weather. For space flight, we have launch capacity, minimum spacing between orbital vehicles, inclement weather on Earth, unfavorable celestial connection. So that's it for the introduction to queuing theory, and have a good day.